Myself, Dr.P.Vijayakumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see exponential random variable. So, it is a type of continuous random variable. So, at the end of this particular session, we will be able to learn two learning outcomes. First learning outcome is understand the exponential random variable definition and mathematical definition, probability density function distribution and applications. Later on, we will see the applications of exponential random variable for solving real-time problems. So, a random variable is said to be exponential random variable if it follows the density function fx of x is equal to 1 by b e power minus of x minus a by b if x is greater than equal to a and is equal to 0 when x is less than a. So, this is the exponential probability density function. Any random variable which follows this kind of density function, we term it as exponential random variable. So, when you see the plot of exponential random variable, so the exponential random variable is a decaying function. Decaying starts from a when x is greater than a and its maximum value is equal to 1 by b. So, in a special case, if a is equal to 0, the density function will be reduced as fx of x is equal to 1 by b e power minus x by b. So, if lambda is equal to 1 by b, this is the function under special case when a is equal to 0. Similarly, the distribution function. So, the distribution function can be obtained from the density function by doing the integration. So, integration of exponential density function gives the exponential distribution function. So, the exponential distribution function after doing the integration, so when x is less than a, it will be 0. When x is greater than or equal to a, it will be 1 minus e power minus of x minus a by b, and when x is equal to infinity, its value is equal to 1. That means it is a increasing exponential function and it will reach the maximum value 1 when x reaches infinity. So, this is the distribution function for the density function. In the special case, if a is equal to 0, the function will be 1 minus e power minus lambda x, provided lambda is equal to 1 by b. So, you can see that distribution function is a increasing exponential, whereas density function is a decaying exponential. So, where do we use this exponential random variable in practical scenario? So, in practical scenario, the exponential random variable is mainly used for modeling the waiting time until an event occurs, especially for a memoryless process. For example, coming to the applications in communication systems, the call arrival time in telephone and mobile networks comes under the category of exponential random variable. Similarly, packet arrival in data networks, service time modeling in queuing systems. So, also we use this concept in reliability testing. So, reliability engineering time for the failure of an electronic component, modeling the system with a constant failure rate, mean time between failures. So, for all these modeling applications also we use the exponential random variable. And also in signal processing application we use particularly for envelope detection in radar and sonar systems, envelope detection, modeling energy of noise samples and also the interval arrival time of random pulses. So, in queuing theory, the customer waiting time in the banks, hospitals, call centers or parks. So, all this comes under the category of exponential random variables. So, there are many more applications for exponential random variables. So, these are some few examples of exponential random variables. Let us solve the problems related to the exponential random variable. We will see one by one real time problems. Okay. The time required to complete a work is exponentially distributed random variable with lambda is equal to 1 by 2. Lambda is nothing but the average rate. Average rate lambda is equal to 1 by 2. What is the probability that the time to complete work exceeds 2 hours? So, firstly, before starting the problem, we need to define the random variable. X is a random variable which indicates the time to complete the work. Okay. Now, given that it is an exponential density function, we need to recall the definition of mathematical definition of exponential density function. Fx of x is equal to e power minus lambda x, where x is greater than or equal to 0 and is equal to 0 otherwise when x is less than 0. So, after defining the exponential density function, and what we need to do is we need to compute the probability that the time required to complete work exceeds the 2 hours. That means probability of x greater than 2. Probability of x greater than 2 can be written as 1 minus probability of x less than or equal to 2. So we know that probability of x less than or equal to x is distribution function. So 1 minus fx of 2. So the distribution function for exponential random variable is 1 minus e power minus lambda x. So applying that 1 minus e power minus 2 lambda, we will get e power minus 2 lambda. But given that the average rate lambda is 1 by 2, substituting we will get e power minus 1 by e, which is mathematically equal to 0.3737. So 37% chance is there to complete the work that exceeds the 2 hours. Next, one more problem which is related to the washing machine. The number of years the washing machine functions is approximately exponentially distributed with lambda is equal to 1 by 10. What is the probability that the washing machine will work after an additional 10 years? So given that the average rate is 1 by 10, average rate is 1 by 10. Now we need to compute the time. What is the probability that the working after additional 10 years? First, x be a random variable which indicates the time or years the washing machine work. Already it is being worked. Now we need to compute the probability that it will be working after additional 10 years. That means probability of x greater than 10. So the probability of x greater than 10 can be probability of x greater than x can be written as 1 minus probability of x less than or equal to x. So using this formula 1 minus fx of x. Now we need to compute 1 minus fx of 10. So the distribution function is 1 minus e power minus lambda x. So you will get e power minus lambda x. So given lambda is equal to 1 by 10. So substitute in that again we will get e power minus 1. Okay, again there is 37% chance for the washing machine to work after 10 years. Next problem is related to the car. The number of kilometers that a car runs before its battery wears out is exponentially distributed on an average of 10,000 kilometers. 10,000. So lambda is equal to 10,000 kilometers they have given in the problem, and given that it is exponentially distributed. So if the owner decides to take a 5,000 kilometers trip, what is the probability that he will be able to complete his trip without replacing the car battery? Assume that the car has been used for some time. So the lifetime of the car is given, the lifetime of the car of battery is given. The battery works up to 10,000 kilometers on an average. Now if the owner wants to take a trip for 5,000 kilometers, now what is the probability that he will able to complete his trip without having to replace the car battery? And the given data is, it is an exponential random variable. For exponential random variable, the density function is lambda into e power minus lambda x. Given average rate 1 by lambda is equal to 10,000. So given an average rate 1 by lambda is equal to 10,000, density function is this one. So replacing lambda with 1 by 10,000, this is the exponential density function. Now we need to compute what is the probability x greater than 5,000 kilometers. So here we are using the probability of x1 less than x2. If I want to compute the probability between any two limits, what we need to do is, we need to integrate the density function over that limits using this formula. So what is the probability that it will exceed 5,000 kilometers, 5,000 or more? So more I am taking it as infinity. So 1 by 10,000 e power minus x by 10,000 dx. Here we know that the formula integration of e power minus ax is e power minus ax by minus a. Using this formula, calculating, what we will get is e power minus 0.5. So it will be 0.6065. There is 60% chance that the car can exceed the 5,000 kilometers. Next one is problem related to the car tire. The mileage that the car owner gets with a certain kind of radial tire is a random variable, given that it is following an exponential distribution. Given the mean value means 1 by lambda given. So on average, a car tire works efficiently up to 40,000 kilometers. Now they are asking us to find the probability that one of these tires at least 20,000 kilometers. At least 20,000 kilometers means probability of x greater than or equal to 20,000. The minimum is 20,000. So using the property of the density function 20,000 to infinity fx of x dx we can do. Doing that we will get 0.6065. There is 60% chance. Another problem is, what is the probability that one of this tire will last at most 30,000 kilometer? At most 30,000 means maximum 30,000. So, maximum 30,000 means the limit is up to 30,000 only. The minimum value we can take here as 0. The maximum limit is 30,000. So, again 1 by 40,000 e power minus x by 40,000 dx. So, doing this calculation using the formula integration of e power minus ax by minus a, what we will get is 0.5270. That means there is 52.7% chance for the tire to last up to 30,000 kilometer, whereas the tire at least 20,000 kilometer, the chance is 60.65%. So, all these values depends on the average rate of the tire. So, the statistical data of average rate of the tire decides all these probabilities. We will take one more problem which is related to the applications of the reliability. So, the mean lifetime of a component is given. So, the mean of exponential PDF is 1 by lambda. So, we know the mean formula E of x is equal to minus infinity to infinity x into fx of x dx. So, using this mathematical relation x into lambda e power minus lambda x, and the range is from 0 to infinity. Doing this integration, we will get the mean value as 1 by lambda. Every time mean is given to us, we need to assume the mean as 1 by lambda is equal to 1000. That means lambda is equal to 1 by 1000. The mean lifetime of a component is given. Now, what is the probability that it lasts more than 1200 hours? That means x indicates the lifetime of the electronic component. The probability of x greater than 1200 we need to compute. The probability of x greater than 1200 can be computed 1200 to infinity lambda e power minus lambda x dx. So, after solving this one, we will get e power minus 1.2. So, it will be closely equal to approximation 0.3010. There is 30% chance that the component will last more than 1200 hours based on the mean lifetime. Here the mean lifetime is less than the targeted question. Here the mean lifetime is 1000 hours. Now, we are asking when it exceeds more than 12,000 hours. So, there is less chance. So, when the targeted question is less than the mean value, then there is more chance. So, the mean value is deciding here the probability. This problem is related to the customer's waiting time at banks, parks, or any queuing theory. The problem related to the queuing theory. Given the lambda is 0.5 customers per minute. The probability of waiting time less than a given time. Now, what is the probability that the waiting time is less than 4 minutes? So, let x be a random variable which indicates the waiting time in minutes. Clearly, any problem which is related to queuing theory or waiting time, it will comes under the category of exponential density function. So, the exponential density function is lambda into e power minus lambda x when x is greater than or equal to 0, or the distribution function is 1 minus e power minus lambda x. So, given lambda 0.5 customers per minute waiting time. So, the distribution function will become e power minus of 0.5 x. Now, what is the question being asked is, what is the probability that the waiting time is less than 4 minutes? So, clearly this formula is nothing but the distribution function. Probability of distribution function is probability of x less than or equal to x, any value we can assume it as a distribution function. The distribution function is 1 minus e power minus 0.5 x, but here the x is 4. So, 1 minus e power minus 2, its value is 0.8647. So, there is 86.47% chance is there, the probability that the waiting time is less than 4 minutes. So, every time a problem is given, what is the thing we are doing is, first we need to define the random variable, later on we need to identify the application, whether the application is related to the exponential random variable or not. First we need to do it. After identifying the application related to exponential random variable, we need to note down the density function as well as the distribution function of the exponential random variable. Next, we need to check for the data in the problem. Any data which is related to problem is given, like a mean value. Mean value is 1 by lambda. So, we need to check for all these details, mean value 1 by lambda, like this. So, once we know all this data, once we identified the application related to the problem is exponential random variable, we need to recall the density and distribution. So, we can solve by solving using simple integration and differentiation. So many real-time examples will be there with respect to the exponential random variable. So, we have seen different examples related to exponential random variable, like queuing, reliability, failure rate. So, we have seen 3 different variety of problems which are related to the applications of exponential random variable. So, here what we have seen is we have defined the exponential random variable and we have seen the problems related to the exponential random variable. So, in the next session what we will do is we will see the operations on the random variable. So, operations in the sense we will see what is meant by expectation, what is the mathematical definition and what are the properties of expectation, and we will see some problems related to the expectation, real time problems. Okay, thank you.